Good day everyone, we are from Group 6 and today we are going to present about the transport properties of gases and its application. Our group consists of 5 members and here are they. So for the first transport properties of gases will be diffusion. Diffusion can be defined as the transport of matter, where the matter will migrate down the concentration gradient, which is from a high concentration region to a low concentration region. As a result, the concentration will equalize throughout the available space, as shown in the diagram at the bottom right corner below. There are a few factors that can influence diffusion, for example, the concentration gradient, temperature, and the size as well as the mass of the gas molecules. Therefore, the diffusion rate can be increased with increasing in pressure, increasing in temperature, as well as decreasing in size of molecules. Fick's first law relates the diffusive flux to the gradient of concentration. It also postulates that the flux goes from a region of high concentration to a region of low concentration, with a magnitude that is proportional to the concentration gradient. Therefore, the law can be written in the form as shown below here, with all the unknowns mentioned below too. D is the diffusion coefficient, which can be calculated with the formula D is approximately equals to 1 over 3 multiplied by the mean free path multiplied by the mean speed. So, to be clear, the concentration is actually very steeply with position. If there is a huge difference in concentration, the diffusivity and the diffusion flux will be very great and hence the diffusion will be very fast. On the other hand, if the concentration is uniform, the difference in concentration will be zero, therefore there will be no net flux.
I would like to introduce the second transport properties, which is thermal conductivity of gases. Thermal conductivity is the migration of energy down a temperature gradient, and it refers to the ability of a given material to conduct or transfer heat. It is generally denoted by the symbol kappa. According to the kinetic model of gases, the thermal conductivity coefficient for an ideal gas is kappa equal to 1 over 3 times mean free path times mean speed times molar heat capacity times molar concentration. Fourier law of thermal conduction, which is also known as the law of heat conduction, states that the rate at which heat is transferred through a material is proportional to the negative of the temperature gradient and is also proportional to the area through which the heat flows. The differential form of this law can be expressed through the following equation. Thermal flux or heat flux equals to thermal conductivity times temperature gradient. In general, the thermal conductivity of gases increases with increasing temperature. The thermal conductivity is greater for gases with a high heat capacity because a given temperature gradient then corresponds to a steeper energy gradient. The physical reason for the pressure independence of the thermal conductivity is that the conductivity can be expected to be large when many molecules are available to transport the energy. But the presence of so many molecules limits their mean free path and they cannot carry the energy over a great distance. These two effects cancel. The thermal conductivity is indeed found experimentally to be independent of pressure, except when the pressure is very low, and then thermal conductivity is directly proportional to pressure.
Now, I'd like to talk about the third transport properties of gases, which is viscosity. The viscosity of gases involves the transport of momentum from one layer of gas to another layer and eventually attains an equilibrium state. And the viscosity coefficient is a measure of resistance to the flow of the gas. The unit of viscosity is poise and equal to 0.1 kg m power minus 1 s power minus 1. The unit of viscosity for gases usually written in micropoise. Viscosity depends on the temperature. This is because the mechanism of momentum transfer is through collision based on kinetic theory. Higher temperature allow greater collisions and thus greater viscous drag. And surprisingly, it is experimentally found that over a very wide range of density, gas viscosity is independent of the density of the gases. Assuming that the gas between two plates is made up of layers and moving at different speed, the bottom plate is stationary while the top plate is moving at speed v0, and the separation of plates is constant. The layer of gas close to the moving plates will move at similar speed as v0, while the layer of gas close to the stationary plates moves slower due to their lower momentum in the x direction. The change in velocity is perpendicular to the flow direction. Therefore, the formula of the flux of momentum is J momentum equal to negative eta dvx over dz.
Transport properties can be found in a wide variety of applications, and one of the applications that relies on the transport properties is the heat exchanger. A heat exchanger is a device that involves the transfer of heat between two or more fluids that are at different temperatures, which is, the heat is transferred from a higher temperature fluid to a lower temperature fluid until a thermal equilibrium is reached. It facilitates the efficient exchange of thermal energy while keeping the fluids physically separated by a heat conducting surface. As the diagram shown, the hot fluid and cold fluid are usually introduced into the heat exchanger through separate flow paths, and they are then separated by a heat transfer surface and undergo the heat transfer process against the temperature gradient. Once the heat transfer process is completed, both of the fluids will exit the heat exchanger through their respective outlets. Heat exchangers also works based on the principle of conduction, convection, and radiation. Some of the common examples that utilize the heat exchangers includes refrigerator, air conditioning system, gas boilers, and also car engines. For example, in a gas boiler, there is a heat exchanger that allows the transfer of heat from the combustion gases to the water circulating within the system. In a gas boiler, hot combustion gases are produced, and they are then flowed through a series of pipes in a heat exchanger while the water circulates around them. As the hot combustion gases pass through the heat exchanger, the heat is transferred from the gases to the water on the other side of the heat exchanger through the walls of exchanger. The temperature of the water will then be increased and are ready to be supplied for domestic use, while the cool combustion gases will be expelled outside.
Now, we have looked at a few transport properties of gases and its applications previously, so I'm going to sum up some important points of this topic. Firstly, we have diffusion, which is the transfer of matter from a region of higher concentration to a region of lower concentration in the absence of backflow. The driving force that causes the transfer of the matter is the concentration gradient. The next transport properties of gases is thermoconductivity. It is the transfer of heat from a region of high temperature to a region of lower temperature. Lastly, we have viscosity. Viscosity is a transfer of momentum from a region of high velocity to a region of lower velocity, which gave rise to the phenomenon of viscous flow. We have looked at the applications of transport properties of gases, which is heat exchanger before this. Heat exchangers are devices designed to transfer the heat between two or more fluids while keeping them physically separated. The transport properties of fluids play a crucial role in the performance of heat exchangers. The main transport properties that affect heat transfer in heat exchangers are: firstly, thermoconductivity. Thermoconductivity is a measure of a fluid's ability to conduct heat. It represents the rate at which heat is transferred through a material by conduction. So fluids with higher thermoconductivity can transfer heat more efficiently in a heat exchanger. Secondly, viscosity. Viscosity is a measure of fluid's resistance to flow. It affects the pressure drop in the heat exchanger and the overall fluid flow characteristics. Higher viscosity fluids tend to have higher pressure drops and lower flow rates, resulting in reduced heat transfer rates.